Yes, we still get 42 meters.
Okay, very good. We still get 42.22 meters, right? All right, give yourself 5 points on that one. Guys, it's still, you will get the same answer. Except notice that we don't have to worry about numbers. It's straightforward. Still 140 feet, give and take. All right. So you guys saw what I did. I end up showing a lot of work, back and forth, and then we do a lot of back substitutions. All right. It's because normally I would do this using half a page. It's very straightforward. All right. So here's your homework. When I give you your homework, you know, it's going to be a test question. Your test question is going to be similar to this. I want you to redo this. I messed it up. I want you to redo this for part B. Okay, so that's your homework. All right, so which means that you will have to use GGG for part B. You can either use this or you can use this. And this one is easier to use. All right, so that's what you need to do. And your test question is going to be similar to this. All right, so conceptually, here's what I would ask. Okay, so SUV versus car, which one comes to a stop sooner? Your common sense is going to say the car. Okay. In reality, because your argument is because it's got less mass, it's got less inertia, which means that it's going to require less force for it to come to a stop, right? And you can also argue that the SUV is going to come to a stop sooner because it's more massive. More massive means it's got a larger apparent weight, which means that the friction it's experiencing is going to be larger. Notice that physics allows you to make two contradictory arguments. If you can justify two opposing views using physics just as well, then more than likely neither view is correct. That's what it means. Okay, so the SUV is going to be heavier than the car, therefore it's going to experience more friction. If the SUV is twice as heavy, the frictional force is going to be twice as large, which means that both of them will come to a stop at the same time, all right, because friction is what brings you to a stop. If the vehicle is 10 times heavier, the frictional force is going to be 10 times larger. So provided that they have the same initial speed, both vehicles will come to a stop at the same time while skating the same distance. That's what it means. And mathematically, you realize that the mass also gets canceled out. Okay, so the math agrees with you. Notice that the masses will not matter. Of course, it's a mathematical argument. I'm more interested in your conceptual justification of it. So which one comes to a stop sooner? Both at the same time. Okay, so now that we made this argument, so which one is going to come to a stop sooner? Is it the train or is it the car, if that's the case? What do you think?
Car.
Okay, so Jack, you said the car. Why did you say the car? Given the fact that we said the mass doesn't matter.
Because that's not what matters here. What matters here is that the car is rubber on concrete while the train is steel on steel.
Beautiful. Give yourself 20 points. What matters here is absolutely correct, guys. What matters here is the coefficient of friction. Rubber on concrete is, in this kinetic case, well, it's getting a 7.85. And steel on steel is going to be, for a dry surface, obviously, it's not going to be lubricated. So it's going to be 0.48. So the traction goes down, guys. The traction goes down. Okay. Now, there's a statement here that I want to test. The statement is that
60 miles an hour.
This thing is going at 60 miles per hour.
Might take a mile and a half to come to a halt.
Is that true? Is it going to take a mile and a half for it to come to a stop? Okay. Most of you guys thought that makes sense. Okay, so let's take a look if that's the case. All right, so train. Let's take a look at the train. The mass doesn't matter, so we're not going to focus on the mass of the train. Okay, the only thing that's going to matter here is the kinetic friction, right? And in the case of the train, that's 0.48. I was looking at it. So everything else is going to be the same as before. So this is G. Okay, so let's use roughly about 10. And once again, the train is moving at 60 miles per hour. So this is 60 miles per hour, same speed, right? All right, so that's the same as 26.78 or 79. Okay, so you got your numbers. All right, so we got all the numbers. So plug those numbers into this and tell me what that distance is for the train. All right, so what do you guys get for this one? So car is 140 feet roughly. What we get? What do you think we get for the train? Train is coming. Okay, so it's about 74 meters. I think that's reasonable. Okay, what is that in terms of feet? All right, so multiply by 3.28. That's 200 and something.
245.
250, give and take, right? All right, so it's going to be 250 feet. If the train were to brake, put the brakes on. Okay, so I need a verification on this number. Okay, it looks to me right. It's going to take longer than the car. There's no question about it, but it's not going to be a mile and a half, guys. It just doesn't make sense.
I get 74.76 as well.
Okay, good. So both of you guys give yourselves 5 points. If this were the case, these trains would always miss their stops. Okay, because you have to start breaking miles ahead. That's not how it is usually. So notice that once again, the stuff that you see on TV is a lot of it is commonsensical. This is written by the writers, basically. Whoever is writing it up.
After the brakes are applied,
There's-
mile and a half, 60 miles an hour. Might take a mile and a half to come to a halt. Miles an hour. Might take a mile.
Might take. This person is making it up, and obviously not sure exactly. It's written by someone
Brake going
doesn't have a physics degree.
60 miles an hour. Might take a mile and a half to come
It takes almost twice as long, but it's not going to take a mile and a half. That's 250 feet.
to a halt after the
It's less than a football field.
brakes are applied. That's the length of 25 football fields.
Not even a single football field. All right, so that's what it is. Okay, so a couple of things that we need to discuss.
Today's cars brake better than ever, but
For coefficient of friction for a regular car, the tire on asphalt, if it's dry surface, it's going to be 1.2 for static friction and 0.85 for sliding friction.
It's up to your tires to translate these advances into stopping power on the road. The Firestone FT70C uses Unity technology to help your car stop when the rain starts. So if you're not driving on FT70C tires with Unity, what's stopping you? The Firestone FT.
Okay, those numbers that we're using from the table, those are just average values. Okay, the quality matters. High quality tires will generate a lot more traction. Okay, I love this commercial because this, according to this commercial, on a wet surface, it's able to generate a lot more traction than a regular tire.
70C with Unity Ultimate Tire Technology.
All right, so when it comes to tires, guys, the quality matters. High quality is going to generate more traction.
Built to stop in the
All right, so that's one of those things. And in physics, we use the average values, but obviously real life is slightly different.
qualifying the
The other thing is the surface area contact doesn't matter.
carefully balanced performance equation was swept away by the onslaught.
The surface area contact doesn't matter as far as physics is concerned.
Qualifying the carefully balanced performance equation was swept away by the onslaught
If the surface area contact doesn't matter, why do race cars have wider tires? How do you explain that?
of rain. Wet track conditions meant the team's strategies for qualifying had to be completely reworked.
All right, so the race cars do have wider tires. So why is it that they do have wider tires if the surface area contact doesn't matter? Okay, let's have a discussion. Just if you want to write something down on the chat, that's fine. If you want to see something, that's even better. Okay, so why do you suppose the race cars have wider tires?
Maybe control,
Okay, explain.
like to make sure like, they don't spin out or anything. It doesn't,
Okay,
it's
so
like a
how did-
turn.
Okay, the wider tires will help you control the car better because. Okay, okay, Dak, I want you to follow what your mind is telling you. Your mind is telling you why, because the wider tires will be able to help you control the car better because they generate more friction, right? That's what you're thinking. All right, because your mind is always going to pull in that direction. Physics says the size of the surface area contact does not matter. So which means that if physics is correct, the wider tires cannot possibly give you more friction. That's what it means. If that's the case, let me ask you this question. If the size of the surface area contact does not matter, why then we don't use bicycle tires on our cars? Okay, I mean, just
Is it
imagine that.
the pressure and the
Okay, very good. Just hold on. That's beautiful. Okay, so imagine that you have these indestructible rims, right? Okay, yeah, they're not going to look as pretty, but then again, you'll get used to it because it's called fashion. All right, and fashion doesn't need to be pretty. As long as everybody does it, eventually it looks normal. Look at 1970s. Anyway, so is it because of pressure?
having a whole different concern for your daughter now.
That's going to be her problem, not mine. Okay, so let's get back. Explain the pressure thing.
The wider the tire, it has to disperse the pressure. It's going at higher speeds, at a higher velocity. These tires, they're made out of different materials than a normal car tire because they reach higher speeds than we do, which also causes temperature increases in the pressure to change within the tire.
Yeah, Chantel, I'm going to give you 20 points for that remark. Guys, what's the difference? Why is it we don't have bicycle tires on our cars? Believe it or not, like 100 years ago when they started building these cars, the tires were not as wide, just remember, okay? They were thicker, wider than the bicycle tires, but I got news for you. They were not as wide as the modern tires are. And then the problem that they had was those tires would blow out within a month, okay? Because you're trying to drive and then there's tremendous amount of drive force acting on the tires. And then what you need to do is you need to disperse that force onto a larger surface area, right? Modern cars usually go around 70, 80 miles per hour. Obviously, there's tremendous amount of force acting on those cars aside from the weight. So what you need to do is you have to disperse it onto a larger surface area in order to reduce the pressure. Now, the race cars go over 200 miles per hour. So you need to take that drive force and then you have to actually disperse it down to a much larger surface area. And I don't know how many laps before they actually change the tires, 100 laps or something like that. I'm just guessing at this point. So the reason why these tires are wider is not necessarily because of friction, but because they're trying to disperse the drive force onto a much larger surface area so that the tires are not, they're not blowing out as easily. Okay, so that's a good enough explanation, but that explanation is mostly correct. I'd say up to 95% correct. But there is more to it than what physics suggests here, okay? Because the sort of physics we're doing is fundamentals of physics. This statement that we're making is true for smooth surfaces, okay? So in terms of smooth surfaces, I'm talking about this tabletop, and then you put something on it which is relatively smooth, like you're looking at this mouse, for example. Okay, so when it comes to tires, it's a little bit different. Also,
New tires were rolled out. Normally, these cars use
okay, so if the surface area contact doesn't matter,
wide treadless tires.
why would they go from treadless tires
The strategy being the more rubber on the pavement, the better the grip.
to the treaded tires? So the strategy is they want to put more rubber on the surface, which means that the more rubber, the better the grip, which means that the larger the frictional forces. And physics says, no, it cannot be true. And the physics will say, absolutely not. More rubber is not going to give you more traction. It's not going to give you more friction.
But the weather changed the priorities. Due to the rain, the team changed to tires with a deep tread, providing better traction in the wet conditions.
The fact of the matter is the surface area contact is going to have a marginal contribution. Okay, the race car drivers know it because they got the best of the best engineers within the field, and they use a lot of physics at the same time. But the contribution of surface area contact, because of the sort of tires that they have, it's very, very marginal, guys. If I'm driving my Ford Tempo, the contribution is almost non-existent. If you're driving my race car, it's going to give you a marginal contribution. These guys want to get every millisecond over the other guy. Yeah, the contribution can be measured in terms of milliseconds. The gain in speed in terms of milliseconds. So for all practical purposes, we will just ignore that marginal contribution. All right, so the surface area contact is not going to contribute to friction, and what little contribution it has is considered marginal, so we will just ignore it. All right, because whatever the claims made by the physics books, it's only for solid, ideally smooth surfaces, okay, and that's it. Real life, yeah, there's a bit of a marginal contribution, but it's so marginal that it's ignorable. All right,